All right, everybody, please be well behaved. We'll give it 2 more minutes. I see you've got the date 2020 down there, Paul.
Yeah, that's the reason.
From last year.
This is when it was supposed to be.
Yes.
By the way, they just started construction on the sidewalk outside my office, so I hope the background noise doesn't come over too badly.
Okay. Here we have 21 people in the audience. But we're up to 60 people online. Well, I suppose we should try and keep on schedule. All right, everyone, welcome back to the second talk of our afternoon session here at Condensed Matter in the City, curiously located this week out at Skye, which is not very much of a city. Let me tell you a few words about our second speaker this afternoon. We're delighted to have Paul Canfield. Paul is the Robert Allen Wright Professor at Iowa State University. He's also a senior physicist at Ames Laboratory at the same location. Paul, since he was a postdoc at Los Alamos, has made major contributions to the physics of superconductivity, such as magnesium diboride, iron-based superconductors, also heavy fermion systems. He's worked on quantum criticality, made beautiful large crystals of quasicrystals, spin glasses, and metal insulator transitions. Paul has been the recipient of various awards, such as the DOE Lawrence Award for Condensed Matter Physics in 2011 and the James McGroddy Prize for New Materials from the American Physical Society in 2017. So he's also really well known for giving great talks. And so we're looking forward to his talk this afternoon, Synthesis as the Heart of New Materials Physics. And we've got 90 minutes for this, but we're hoping to spend half of it on discussion. Thanks very much, Paul, and go ahead.
All right, well, thank you, Piers. And thank you all for attending and for organizing this. This is a meeting that, as Piers pointed out, was originally supposed to be 2020. And the organizers were very diligent about this. In January of 2020, they had us register and do things. And we were told it was going to be on this beautiful island. And I got all excited and looked at it. And Piers even showed us one of these views on his laptop a moment ago. Unfortunately, things don't work out. So instead, I have a beautiful view here at Iowa State University and Ames Laboratory. That's the view out my window, Piers. But all of that said, I really want to thank the organizers for working hard to get this lovely meeting together through all of these difficult changes. And if anyone can speak Gallic or read Gallic, I'd appreciate if they pop in and read what's in red here, because I will brutalize it. Anyone going to help out? No. Okay. All right. Well, next year in Scotland, I hope. All right. With that said, let me start with my conclusions, okay? I really think the design, discovery, and growth of novel materials is the heart and soul of that area I call new materials physics. I think that synthesis combined with broad and eclectic interest in materials and ground states are going to be what's necessary to really help solve humanity's problems. Either we're going to solve these by discovering new materials, or the horse riders of the apocalypse are going to end up mounting up again. And we've seen a few of them recently. And it's our charge to refine, utilize, and employ this powerful tool and teach it to as many different people as possible. Now, just to confirm that I haven't lost people, am I still online? Can people hear me?
Yes.
Good to
Yes,
hear
okay,
you.
thank you. Good. There was a beep and I was thinking, oh God, I dropped out. All right, good. So for luck or for iron, let's start with horseshoes, okay? And the reason I want to start with horseshoes is in politics, there's a horseshoe theory of politics, which basically says the far left and the far right are not on extremes of a linear scale. They're actually much closer together than you might appreciate. And you're welcome to put in your own examples here as you want. And that's sort of the end of political statements for me. On the other hand, I think there is a horseshoe theory of physics. And at some level, John Chalker this morning mentioned it in the sense that he felt that our talks were going to be almost at opposite extremes. I think actually exploratory synthesis and closed form theory are a lot closer than they apparently might appear as well. And that's because I know theorists who explain to me that you can go from, for example, electron-phonon theory of superconductivity to inside a neutron star to a quark-gluon plasma just by changing a prefactor. It's trivial, I'm told. Okay. Now, that might be trivial for certain theorists. On the other hand, what is trivial for me as an experimentalist is to say, look, I can actually take a motif. This is the Half-Heusler structure, rock salt +1, and I can just decorate different atoms on this motif and go from titanium nickel tin, which is a 1 eV gap semiconductor, to manganese nickel antimony, a 700 Kelvin ferromagnet, to a terbium bismuth platinum, the heaviest heavy fermion, or lutetium bismuth platinum, a proposed topological insulator. Okay, and that is trivial. Okay? Now, the neat thing, the advantage of synthesis over closed form theory is instead of just dreaming about what might be, we get actually to interact and manipulate our ideas as they become physical reality. Okay? So what do? What we try to do is project a Hamiltonian onto a periodic table and then actually grow something. Now, that's sort of grand glorious and a little abstract. Let me try to quantify it a small amount. Okay, so here's superconductivity. We can take light elements that have tight bonding and high phonon frequencies. We can imagine transition metals that have high density of states. That's what would dial in a good superconductor and electron-phonon mediated superconductors. We could also say these transition metals possibly host fragile magnetism. By substituting an alkali or alkali earth, we can tune band filling. By going up and down columns, for example, the pnictides, we can tune band width. We can have local moments in the middle of the lanthanides. We can have fragile moments on either end. This is what I mean by projecting a Hamiltonian onto the periodic table. We can take ideas and terms and try to figure out where on the periodic table they may live. Okay. Now, having said that, the number of potential compounds is still huge. Okay. Even if we get rid of the noble gases and the hot elements, we still have about 80 elements to play with. And the problem is then if we do simple estimates on number of potential binary or ternary compounds, let alone quaternaries or alloys and substitutions, we end up with millions or tens of millions of possible materials. And that's just too big of a phase space for blind combinatorials. So how do we choose what we want to make? Okay. What I want to do in this talk is to give you, and you in particular, hopefully postdocs, grad students, some of the younger folks, not the Bobingers who are old and gray, okay? Let's try to figure out how to coax the unicorn out of the forest. Let's try to encourage visions of sugar plums to dance in our heads, or if not sugar plums, maybe other delightful things, okay? What I want to do is I want to give you an idea of how to create ideas for new materials and then try to get them to manifest themselves. And this is the tricky part of research, okay? So for my own group, and here is a pre-COVID picture of this rogues gallery. we try to narrow phase space in 3 different ways. And what I want to do in this talk is go over each of these, all right? Sometimes you want a specific compound. Sometimes you want a specific ground state. And sometimes you want to just search for known and unknown unknowns, okay? And what I want to do is give you an idea of how these overlapping motivations flow into each other and interact with each other. Okay? And these are precise. As you can see, they sort of blur into each other. But these are basically the different motivations for trying to make and understand something. So we can start with wanting a specific compound. This is really the easiest. It reduces phase space dramatically because you can take the idea of want a specific compound projected on the periodic table, and it's a delta function, a specific compound. Okay? Now, it's often a compound that's hopefully the birth of a new field or going to allow you to ask and address very specific questions. So let's start with this. This is sort of the easiest, most conspicuous motivation, and then we'll look at the other 2. So we'll look at examples. We'll look at rare earth nickel boron carbides, rare earth magnesium zinc, MGB2, and the iron arsenide superconductors. All right. It's worth noting that in each of these cases, the very strong desire to have that specific compound led us to extend our growth techniques and capabilities, and this then gets plowed into the mix and it helps us do more and more diverse things in the future. All right, let's start with the boron carbide. So in 1994, there were 2 related families of, at that point, relatively high temperature superconductors. Yttrium palladium 2 boron 2 carbon and lutetium nickel 2 boron 2 carbon with TCs of 23 and 17. The 23 rivaled the highest electron phonon TC at the time. So it was really quite interesting. It gave a hint there was still some gas left in electron phonon superconductivity. So at the time, we really wanted to grow the lutetium nickel boron carbide because this was stable as opposed to metastable. Now, it's a tricky growth. It's a quaternary. It's refractory, it's incongruently melting. All we were missing was toxic and radioactive for, the full 5-fold don't try this at home category. But these we could manage. So what was nice is nickel and boron have high melting points by themselves, but have this cascade of eutectic valleys. So this offers a region where we might be able to grow samples. Indeed, what we did is we developed a 2-step process where we would cool from 1500 to around 1200, crash to room temperature, seal in silica, reheat to 1200, and then be able to decant and get beautiful single crystals of lutetium nickel 2 boron 2 carbon. And if we studied it, we could see that it indeed has a TC around 17. It has a fairly isotropic HC2, but a rather low one. So this was sort of disappointing for applied superconductivity. On the other hand, if you can form something with lutetium, you can usually form it with the other rare earths. And indeed, thulium, erbium, holmium, dysprosium have coexistence of superconductivity and local moment rare earth magnetism. And these materials became a playground for understanding the interaction of large local moment magnetism with superconductivity. It's sort of the opposite extreme of the magnetic superconductors we see in the cuprates or in the iron-based materials. Now, as we have a progression, we go from wanting a specific compound to wanting to study a specific ground state, the superconductivity and its interaction with antiferromagnetic order. But in many cases, you can have unknowns or surprises. And in the case of the boron carbides, the surprise was the fact that they were the first examples of a hexagonal to square flux line lattice transition due to non-local considerations. So as we increase the field, we could see the Abrikosov-Volkov lattice going from a hexagon to a beautiful square. All right, now let's look at another example of wanting a specific compound. In 1997, we became interested in growing rare earth magnesiums in quasicrystals to study their magnetic properties, okay? All prior samples had been polycrane and even worse, polyphase. So we really wanted to try to get these materials under control. Now, we were able to access an exposed liquidous surface to grow these. So we could cool down a melt rich in magnesium and zinc and intersect this liquidus for growing the quasicrystalline phase. We were able to refine this phase diagram. Now, what this required, though, was us to work with a solution that's rich in magnesium, which means that we had to change from using alumina and silica to tantalum and develop a way of straining and decanting tantalum growths. Okay. Now, with that done, we were able to grow beautiful single grain quasicrystals. These were some of the first large, naturally faceted icosahedral quasicrystals. And in addition to being incredibly aesthetic, and this became one of the sort of archetypical images of these, we were also able to do the basic physics on them. So we could grow these for non-magnetic yttrium, non-CEF split, in other words, Heisenberg-like gadolinium, and terbium through erbium. And what we were able to find was, with these highly ordered, albeit aperiodic sublattices of rare earths, we could have classic model spin glass physics. Okay? Now, if I end up saying something's a model system, it's sort of fair to say, well, then use it to ask very clear or clean questions. And with these materials, we were able to ask the question of, is there a difference between a Heisenberg and non-Heisenberg spin glass? So what we were able to do is look at the rare earth mag zinc for erbium, holmium, dysprosium, terbium, gadolinium, and look at two dilutions, yttrium, terbium, and yttrium, gadolinium. If we look at the paramagnetic theta value, we can scale this with the de Gennes factor, and we can see beautiful linear behavior, which is exactly what you would hope for and anticipate. We can also measure the freezing temperature and plot the freezing temperature versus the theta, two experimentally measured quantities. And we can see this break up into two very clean manifolds, a Heisenberg manifold for the gadolinium and the gadolinium dilution with yttrium, and a non-Heisenberg manifold. Okay? Now we can understand this if we have a simple analogy. We can say if a floor is covered with perfectly spherical marbles, it's slippery. On the other hand, if we make marbles non-spherical, then the floor will be less slippery and more inclined to seize up. Okay? In a similar way, a spin glass comprised of Heisenberg or spherical moments for the gadolinium freezes at a lower temperature than the non-spherical or the CEF split ones. And that's what we're seeing here. Now, in addition to this, we get a key insight that for spin glasses, we can replace the word random with aperiodic. And that's sort of the point I was making at the end of John's talk as well. You can sometimes, with quasicrystals, appreciate that it's not really randomness that's needed. Aperiodicity will do, even in a highly ordered system. All right. So for in the rare earth magnesium zinc quasicrystals, again, we went from wanting a specific compound to wanting to study the physics of a specific system to then seeing the effects of CEFs on spin classes. All right. In 2001, there were rumors that MGB2 may superconduct near 40 Kelvin. Now, this was beautiful, but when we go to the binary phase diagram, we see that there is no simple way of growing single crystals of MGB2 from the binary. There is no liquidus line that we can access. You essentially immediately precipitate out fine polycrystals. Now, despite hundreds of growths of binary, ternary, quaternary, it is not simple to grow single crystals of MGB2 at ambient pressure. You can go up to several gigapascals and get them, but that was later. On the other hand, as physicists interested in the science of superconductivity in this material, we'll measure what we can. So we devised a way of growing high purity polycrystalline samples. And in this case, what we could find is that in as little as a few hours at 950, we can have magnesium vapor diffuse into high purity boron, and we can get high purity MGB2. And since we had high purity isotopic boron around, we can immediately look at the isotope effect. We can see it in magnetization and resistivity and specific heat. There's a 1 Kelvin shift in TC as we go from boron 10 to boron 11, and this was fully consistent with phonon-mediated BCS. So the first paper published on MGB2 immediately made it clear that this was an extreme example of phonon-mediated superconductivity. Now, with samples like this, then we can measure out HC2. We can see it's a very good metal. We can see HC2 is relatively modest for the pure material, and has a moderate anisotropy because we developed a technique for inferring anisotropic HC2 from polycrystalline samples. Now, with that said, we went from wanting a specific compound to actually very much wanting to see if we could modify or improve superconductivity in MGB2. And the reason we wanted to do that is because niobium-3 tin was the industrial standard for superconductors. David Larblestier and co-workers eked the last Teslas out of HC2 here through Herculean efforts. Pure MGB2 has a much higher TC, but has a very low HC2. And what we wanted to do was see if we could increase this HC2. And indeed, by titrating carbon onto the graphitic boron layer, we could see HC2 increase as we went from 1%, 2%, 3%, 4%, 5% carbon substitution. We very weakly suppress TC, but we dramatically increase HC2. So we have carbon-doped MGB2 superseding the HC2 of niobium-3 tin over the whole temperature range. And perhaps more importantly, we have this region at around 20 Kelvin, which in subsequent years has become known as the MGB2 zone of use, where we can actually have superconductivity where niobium-3 tin hasn't even turned on. We can have superconductivity at the temperature a very simple displex, a closed cycle refrigerator can cool us, and we can have HC2s as high as maybe 10 or 15 Tesla. So what humanity has done in the subsequent 20 years is moved from treating MGB2 as a remarkable discovery to treating it as an applied superconductor. We can make multi-filamentary wires. We can wind kilometer lengths into Helmholtz-like coils, and you actually have MRIs now based on MGB2 technology. They can have open access and can be cooled much more cheaply and efficiently. So a final example of one specific compound, and then we will go to the more interesting motivations, okay? In 2008, we wanted to grow pure or potassium substituted barium iron 2 arsenic 2, okay? Within 14 hours of a Yorent posting that polycrystals of barium iron 2 arsenic 2 doped with potassium could superconduct, we were able to have single crystals. We were able to grow crystals that then allow us to look at the anisotropic properties. So we immediately measured HC2. We can see that for up to 14 Tesla, we're suppressing TC only by a tiny amount. So we know that there are going to be very large HC2s. In addition, we have a fairly modest anisotropy. So with these data, we were able to immediately go to the National High Magnetic Field Laboratory and measure it to much higher fields. And we can see that we have A, very large HC2s, B, decreasing anisotropy. And if we remember that 20 Kelvin was a big deal for MGB2, here, if we look at 20 Kelvin, the lower HC2 is in excess of 40 Tesla. That's higher than what any of these guys get at base temperature. So it immediately indicates that these have the possibility of being practical superconductors themselves. All right. Now, often, as we've seen, success in wanting a specific compound can lead to wanting a specific ground state or wanting to search for known or unknown unknowns. Let's look at that a little more carefully with this case, and then we can look at these as starting points in their own right. So, starting with barium iron 2 arsenic 2, we wanted to determine the range and the rules for superconductivity. So this is wanting to study a specific ground state. We can start with iron, and we can then say, fine, let's see what happens as we substitute in various 3D transition metals. And we don't need to limit ourselves to 3D. We can go down to 4D or even 5D. The importance of this is that instead of having millions of random compounds, we're now talking about a dozen or less substitution series. This is finite and tractable. And indeed, what we were able to do then is by looking at, for example, cobalt, rhodium, nickel, and palladium substitutions, establish the rules for the road for this type of superconductivity. We could see that this HC2 dome scales with the number of extra electrons we put in. We can see that as we suppress this antiferromagnetic orthorhombic transition, we see them split and separate. we see a dome of superconductivity, and we see a backbending of this transition. This phase diagram, which has become the iconic one for the iron-based superconductors, helped inform the theoretical understanding and motivated our ability to understand these compounds. Now, what about unknowns? Well, we have barium iron 2 arsenic 2, strontium iron 2 arsenic 2. These were both known materials before the iron arsenide superconductors, okay? On the other hand, there was no report of calcium or magnesium. So we tried to grow calcium iron 2 arsenic 2 as single crystals out of tin in the same way we grew barium or strontium. And what we were able to do was discover a new phase in single crystalline form. And calcium iron 2 arsenic 2 turns out to be the extreme member of this series. It has strongly coupled first order antiferromagnetic and structural transition. In addition, if we apply very modest pressures, we can go from a tetragonal to a collapsed tetragonal phase, at which point we lose any hints of the magnetism or potential superconductivity. Now, of course, we can say, good, barium, strontium, calcium, what about magnesium? Well, sometimes when you ask nature a question, the answer is no. So we asked, does magnesium iron 2 arsenic 2 form? And the answer was an unequivocal no, both for my group as well as several other groups that I have interviewed about this material. All right, now that's sort of warm up to introduce the ideas. Let's go to the other motivations because these are where things become more interesting. So I want to give two examples of what I would call negotiating with nature, of wanting a specific ground state and using that desire to then try to narrow phase space. So let's start with a desire to have a praseodymium-based heavy fermion, okay? So praseodymium is an interesting material. It can be ambivalent. If you look at the oxide, it's a mixed valent oxide. It's a mixed 3+, 4+ oxide, okay? On the other hand, praseodymium is non-Kramers. So if you're not careful, it can drop to a singlet ground state, at which point you have no entropy to transfer over to a heavy electron state. So if you're thinking of wanting to have a praseodymium heavy fermion, the first task is to preserve entropy, okay? So if we look at Lilisk-Wolf from 1962, where they plot for cubic point symmetry, the CF splittings of all the rare earths, we can see that a gamma-3 ground state is a gamma-3 splitting is a possible ground state for certain situations. The gamma-3 is nice because it's a non-magnetic doublet. Doublet preserving entropy, non-magnetic, it rules out magnetism as a way of removing this entropy. So sort of a double bonus there. So that being the case, we want to use this insight to aggressively constrain the phase space. So when we were doing this, I would go to Pearson's handbook, which back in those days was actually handbooks. And we can keep in mind the cascade I want to invoke. I want to have a cubic unit cell with a single rare earth site, with that rare earth site in a cubic point symmetry, and then I want the rare earth to be praseodymium, okay? If I can make it through that cascade, I can then check the literature for hints, okay? So if we go through this, I first look at cubic unit cells, single rare earth, make sure the rare earth is in the cubic point symmetry. One of the systems that I come across then is this face-centered cubic, 16 atoms per unit cell, bismuth trifluoride, otherwise known as a Heusler structure, and I come across silver 2 indium praseodymium, okay? This is a material that Rosemarie Galera in Grenoble had looked at in the late 70s, hoping it would be a singlet ground state for praseodymium. It was not, it was a failure. It was a gamma-3 doublet. She published it in a conference proceedings and moved on. God bless her, because that hint, that statement made it clear this might be the material we want. So we were able to reproduce her inelastic neutron scattering. We see gamma-3 is the ground state separated by about 6.1 MeVs. We can take this cascade of CEF splitting and fit our specific heat data to it very well at high temperatures. But at low temperature, something happens. If we look more carefully, we see specific heat coming up, saturating, and then going linearly to zero through 0, 0. So if we plot C over T versus temperature, we see the linear specific heat rising and saturating at 6 joules per mole K squared. That is a very, very large linear specific heat. So can entropy be preserved in a praseodymium-based system to low enough temperatures to allow for hybridization? Yes, if you do it carefully. Cubic unit cell, cubic point symmetry, right CEF splitting. Can a praseodymium system go heavy? Yes, but I think it's fundamentally different physics because this is a non-magnetic doublet, okay? And there have been beautiful measurements by Doug McLaughlin and others really confirming it's non-magnetic. So what we have here is instead of a dynamic screening of a local moment for a condo or a heavy fermion, I think what we're having is a dynamic screening of a desire to have a Jahn-Teller distortion, which is indeed what happens in praseodymium lead-3, which has a similar CEF ground state, but it has a cooperative Jahn-Teller at low temperature that removes all the entropy. So praseodymium silver 2 indium then opened the area of praseodymium-based heavy fermion research and also generalized this idea of preserved entropy as a route to heavy fermion physics. All right.
Question, just to interrupt
Sure.
things. Can you remind us, that do any of these praseodymium systems have doublet ground states? Or are they all singlets?
The whole point of this discussion was we very carefully preserved the
Gamma 3, yes.
doublet.
Okay.
So no, the whole point was I wanted to have this cascade to then see if I could get a gamma 3. And indeed, praseodymium silver 2 indium has that, and as does praseo lead 3. But in this case, we seem to avoid a cooperative Jahn-Teller, and it goes heavy.
So it's entangled with its surroundings somehow.
Well, as I say, my experimentalist image of this is we're dynamically screening with the conduction electrons the predisposition to have a Jahn-Teller distortion. Okay, so if you want to say in a heavy fermion, you would look at the quasi-elastic line width. I think here, what you'd want to do is look at the phonon spectrum and see if something interesting is happening in the phonons as you go into this heavy state.
Thank you.
Yeah. And please, as I go through this, interrupt, chime in, whatever, and then at the end, we can go back and talk about any of the things I go over or open it up to systems that I haven't talked about. For example,
any questions, please don't hesitate to raise your hand in the chat or,
or pipe in.
Pipe in, yeah.
Very good. So let's look at a more modern version of wanting a specific ground state, okay? So the praseodymium heavy fermions, did that a little while ago. Let's look at something a little more contemporary. And it's what I call fragile magnets, okay? And I'll explain the term. So let's say you wake up one morning and have a unique idea. You want more high TC superconductors. Great, that's a specific ground state, right? Now, unfortunately, if I go to my theoretical colleagues and say, I had a great idea, let's find more high TCs, I'm not giving them a lot of guidance, okay? So let's try to refine this idea, refine what it is we truly desire, okay? So let's look at some of the classical families of high TCs. We can look at the cuprates and the iron-based materials, and our superconductivity in each of these cases is proximal to or intersected by a clashing antiferromagnetic ordering, okay? Now, we can then refine our desire. So we can say that in each case, superconductivity is proximal to a fragile magnetic state, okay? A state that we've suppressed to zero, and even as we've suppressed it to zero, in many cases, we see a reduction in the size of the ordered moment, okay? So let's rephrase our desire. Let's say we want to find transition metal-based fragile magnets, okay? Now, we can then start trying to limit phase space, okay? By focusing only on the most likely transition metals. I maintain that the 4 most likely suspects are chromium, iron, cobalt, and nickel. Now, if I'm leaving out your favorite transition metal, you're welcome to look at it. There they are. Even if you want technetium, go for it. I have a colleague in Canada who says he's going to sort of resurrect technetium research. We can do that as well. But honestly, these four are more than enough. And as a matter of fact, if I just look at one, let's say cobalt, we can get an idea of the scope of the problem. Okay, so in this case, we can appreciate that Pearson's crystallography over the past few decades went from these handbooks to being a very convenient computerized database. Okay, you can either do it online or you can have it on your laptop from a disk. Okay, and what you can do then is you can make cuts. So in Pearson's crystallography, I can say, let's just look at a tetragonal unit cell, a ternary compound, and cobalt bearing. Okay, that very limited cut through phase space gives me already over 1,000 compounds. Okay, so if I think of cobalt, well, what about hexagonal or rhombic, monoclinic, or chromium, or iron, or nickel? It's a lot. So we're going to need a way of making this simpler still. Okay, so we can try to get our computational colleagues involved. But again, we need to sharpen our question. Okay, because just saying fragile magnet, again, is not helpful. Okay, so computationally, it's much easier to look at a pure compound under pressure than it is looking at a doped material, because a doped material, you need to do supercells or make rigid band assumptions or all sorts of horrible and degenerate things. If you can look at a pure material under pressure, you're not dealing in other layers of approximation. Okay, now, grossly speaking, this means we're looking at bandwidth more than band filling. But that's okay, because in many of these superconducting systems, we see that the effects of doping, here's cobalt doped barium iron 2 arsenic 2, we suppress antiferromagnetism, orthorhombicity, get a dome of superconductivity. The effects of doping are very similar to the effects of pressure. Here's pure barium iron 2 arsenic 2, we can apply pressure, we suppress the antiferromagnetic orthorhombic, and we get a dome of superconductivity. So maybe we can use computational studies on pure materials under pressure to give us some hint of what might be promising. Now, experimentally, what we can do is we can try to identify promising materials, either through data mining, literature search, gestalt, seat of the pants intuition, or guidance computationally. We can measure magnetization, transport, specific heat, many different quantities up to 1, 2, 8, 20, 50 GPa, depending on the cell or depending on our desires, and help determine the degree of fragility. We can use chemical substitution because experimentally we aren't constrained, and systems that have magnetic transitions that can be driven to zero will be studied in detail, and some of them will be used for benchmarks. Okay? Computationally, we can try to provide benchmark data to our computational colleagues and see if they can capture this idea of fragility or non-fragility in some cases. Once methodologies are considered to be reliable, we can use them to make first cut identifications, and the results are then something that we can test and feed the results back in and try to refine the methodology. Okay, we've started trying to do this. My dear colleague and friend Rosa Valente, who was here for the last talk, I think she's here now, although I can't see who's here in this mode, has been with us on this adventure for the past several years, and I think we're making progress. But it's not simple, okay? But it's important to try to use these ideas to limit phase space. Okay. Now,
Well, can I ask you before we go on, why in your cut did you exclude copper? Was that because you felt it had been explored extensively already? Was there another reason?
Okay, yeah, let me go back here. That is my prejudice. Okay, so if you look, we go back to the green ones, you see copper's there. You can include whatever you want. Okay, now in my cut there, it's because I tend to look at intermetallic spheres. Okay, copper in an intermetallic and a broader band material is almost never moment bearing. You're seeing in the cuprates as oxides, okay, but not so much in the metals. Okay, but again, that's just a matter of prejudice. Okay.
Thank you.
You bet. All right, so let's see if this comes back. There we go. So Fragile magnetism is something that I think Elena Gatti will discuss later on in the week, okay? She has been spending the past few years in very careful studies of pressure and stress on phase diagrams like lanthanum chromium germanium 3 or lanthanum 5 cobalt 2 germanium 3. These are both systems that start out as ferromagnets, and one of the side products of us trying to look for these fragile magnets is we keep stumbling across ferromagnets and bumping our heads and body parts against avoided quantum criticality, which is fascinating but frustrating. We're continuing to try to look at the anti-ferromagnets, but the ferromagnetism has been a very interesting side product of this. And Elena will talk about that, I think, on Thursday. So stay tuned for that. Now, let me get to the third motivation. This is where it gets fun, okay? Looking for known and unknown unknowns, okay? So let's first talk about known unknowns, okay? And I can give two sort of names. We can look at a run across a series, or we can study a family. And people go, what the heck do you mean by a known unknown? That sounds like an oxymoron. And I've been called worse by better, but okay, fine. A known unknown is actually very simple. In rare earth series, so if you have a rare earth XY family, okay, let's say rare earth nickel 2 germanium 2. If you look at the literature, and a few decades ago, the literature had a few crystal structures and very little else, maybe some work on the cerium, okay? But if you know that, for example, crystallographically gadolinium nickel 2 germanium 2 exists, then you can make a pretty good guess that probably terbium and samarium and maybe neodymium and erbium also exist, okay? If the crystallographic data says gadolinium and lutetium exist, even if there is no data, you actually pretty much know that the intervening terbium, dysprosium, holmium, erbium, thorium, and maybe even ytterbium exist. These are known unknowns, okay? Now, what we have done over the decades is look at many different rare earth series where, as you dial in your various rare earths, as you go from lanthanum over to lutetium, or as far as you can go, because some series just sterically are not stable across the whole range. But exploring all of them has led to many discoveries of interesting extreme local moment anisotropy, itinerant magnetism, superconductivity, metamagnetism. In addition, it defines the entries on the menu that you get to choose from. We have found materials that are well-defined Ising-like magnets. We've found materials that are well-defined four-state clock models. If in the future we end up having a physics problem that really needs that type of anisotropy, we know where to turn to. Okay, so that's one type of known unknown. Okay, now we saw another example of this when we were talking about the iron arsenides, okay? So we had barium and strontium, 2 iron 2 arsenic, okay? These are known structures. Then within the same family, we can say, look, it's pretty likely that calcium and maybe magnesium would form. So it's loose vocabulary. This is not well defined, but I consider that sort of part of a known unknown as well. Good. Let's turn to the unknown unknowns. Okay, these are the searches that are a little unfocused. Okay, it's not quite throwing darts at the periodic table. You certainly don't want to confess that to your funding agency, but they're explorations where you're sort of walking off the end of the pier and seeing what's going on. Okay? So let me give you 2 examples of those, something I call deep paratectics and something I call we find solutions. Okay, deep paratectic project. Here's a binary phase diagram for platinum and tin. Okay, so platinum melts at a high temperature, and once we're beyond 50-50, we have this cascade of compounds that decompose paratectically. Platinum tin 4 is a compound that if you actually try to grow it by slowly cooling a stoichiometric melt, you'd first grow platinum 2 tin 3, then platinum tin 2, then platinum tin 4, and end up with a little tin left over. It would be an ugly mess. Okay, so generally materials that have paratectic temperatures that are buried underneath various other features in the phase diagram have not been studied in single crystal form unless they've been grown out of solution. And at least until recently, that meant unless someone from my group or a graduate from my group had actually explored them. So these were a very interesting area of, well, they're probably not explored. We have no idea what physics they may hold, but we can make them and then ask them the question, are you interesting? Okay, so platinum tin 4, we can grow out of greatly excess of tin. Okay, so 4% platinum and 96 tin, heat it up, cool it down. This is a fairly quick grow. You know, it's over the weekend, and you get beautiful crystals. And what we found out is this is a material that is incredibly generous. With very little effort, you can form a material that has remarkably high purity. This is a material that has residual resistivity ratios, the ratio of the room temperature to the low temperature resistivity that can exceed 1,000, all right? Now, that's sort of cute, but what we found is in addition to this, it has phenomenal 500,000% magnetoresistance. It has quantum oscillations in almost any property you choose to look at, okay? So we were intrigued by this in 2012. As time passed, we started to realize, 2016, that in many cases, these extreme magnetoresistances could be associated with interesting topologies. And we went back to it. My colleague, Adam Kaminsky, with his in-house laser ARPIS, was able to find these hosted DRAC node arcs. Okay? And this is a material we sort of grew just as a desire to explore this unknown. Let me give you another example, all right? As we looked at the rare earth transition metal 2 zinc 20 materials, and these are materials that are exquisite, beautiful, lots of good physics. I haven't talked about them at all, but we mastered how to use zinc as a solvent, okay? As a result, when I had 2 undergraduates for a summer, I asked them to look at scandium zinc 12. This is a tetragonal material that I thought maybe might have some interesting scandium physics, okay? Let's look at it. So the first growth, I was with these 2 students when they opened it, and that's the crystal we got, okay? Now, I can assure you one thing, that is not tetragonal, okay? And indeed, you can count the edges, you get the number 5. I called my colleague Alan Golden and I said, it's 5. And he's used to me and my cryptic statements enough that he came down and we started a campaign to understand this new quasicrystal. What we had done is we had discovered the second known stable binary quasicrystal, a icosahedral scandium 12 zinc 88. We redefined the binary phase diagram. I really thought this was not my job, but we had to refine it and correct it for this other paratectic compound. And what we speculated was this quasicrystalline phase is a low paratectic compound adjacent to scandium zinc 12, which is what's known as a crystalline approximant. It has a crystalline unit cell, but it has motifs that are often recognized as being associated with quasicrystalline ordering. Okay. Now, this discovery led directly to the discovery of the rare earth cadmium icosahedral series, because gadolinium cadmium 6 is also a crystalline approximant. And based on this, we were able to make sort of the audacious prediction that if we cool this slowly to low enough temperatures, we would probably grow the cadmium cadmium 6 and get little hexagonal pimples on it as we entered into a hypothesized quasicrystalline phase, and indeed, that's what we found. All right, let me give you another example of unknown unknowns, okay? This is what I call we find solutions, and it's very simple. In order to grow a material out of a solution, you need to have a solution that contains the elements you want to have in that material. And volatile elements are particularly hard to work with. And given what we've discussed today, hopefully you can appreciate that, look, the pnictide series is interesting. Bismuth and antimony compounds are delightful and lovely. Goodness, the arsenides have the iron-based materials, similarly with the phosphides. Well, logically, the clever monkey would say, well, what about nitrogen? Can't we grow nitrogen materials? Well, one of the problems is it's hard to get nitrogen into solution, okay? So what we did was we looked at various binary phase diagrams And there was this reported phase diagram for lithium and nitrogen that alleged you can have a liquid, at 600 or 800 Celsius that has nitrogen in it. Okay, now sometimes these are computationally generated and not accurate. We very carefully approached this phase diagram, and we indeed confirmed it, that if you take lithium-3 nitrogen, polycrystalline, melt it in some lithium, heat it up, slowly cool it, you get beautiful single crystals, and you have a liquid that is actually holding atomic nitrogen in it, because this structure is not made out of N2 ligands that are well separated. So what this meant then was we could start playing around. So we realized this has 2 lithium sites. We tried doping in transition metals just to see what we can get, or can we grow a transition metal nitride? And instead we ended up with a doped lithium nitride, and we found out the transition metals in this rather exotic one-dimensional geometry have anisotropies, CEF split anisotropies that are larger than any known anisotropy for a rare earth. Absolutely phenomenal. Okay? Now, we can also extend this idea to other volatile materials. Okay, so we're interested in trying to find new hard ferromagnets or new fragile antiferromagnets. And one of the ways you can do it is try to discover new crystals that have abundant transition metals, okay, and see what you can find. Many phase diagrams have been explored, but the ones with volatile elements have been avoided. Okay, so what we figured out was we can take transition metals, manganese, iron, palladium, and we can look at the transitional metal rich eutectics. Okay, here's a manganese phosphorus eutectic at about 10% phosphorus. We came up with ways of creating a liquid that does not have large vapor pressure above us and then allows us to try to grow new ternaries. Okay, so what we can do is once we master these binary solutions, we can add third elements and see if we can stabilize or discover new transition metal rich compounds. It's really like inviting the unknown unknowns in for tea. So you're asking nature, gee, does a manganese phosphorus X compound form? And you can discover new materials. And then since it's transition metal rich, it probably will have some magnetism. Okay? So hopefully I've been able to show you that these searches feed into each other and inform each other. In a healthy research environment, what you really want to do is have them just cycling into each other in sort of an endless permutation and cycle. Okay? Let me end with just sort of a summary, a recent example, and then we'll finish. Okay? So in 2016, EO and coworkers found that for large enough C-axis contrast, you could take these 1,2,2 arsenides and create a true quaternary, a 1,1,4,4. So if you mix calcium and sodium or barium and potassium, these are systems that are close enough in size that you get a solid solution on the alkali earth site. Okay, so it's still the 1,2,2 structure. On the other hand, if you have high enough contrast, in EO's paper they use the example of calcium and rubidium. Okay, then you can get a true quaternary where you have layers of rubidium, layers of calcium, layers of rubidium, layers of calcium. Okay, when we saw this discovery in polycrystalline form, we really wanted to make this compound master. So the first thing we wanted to do was see if we can make single crystals. Okay, and these two fine gentlemen, William Myers and Tai Kong, spent a couple months actually trying to figure out where we could find the exposed liquidous surface in this true quaternary phase diagram, which we can then map onto a pseudo ternary phase diagram. And by identifying this as a region of primary solidification, we could grow single crystals. Okay? With single crystals in hand, we could look at the basic properties. Okay? This is a material that has simply a superconducting transition. No magnetism, no orthorhomбicity, but it has a beautiful sharp TC. In the single crystals, we could push it up to 35 degrees Kelvin. It has a large and mildly anisotropic HC2, and it's not that different in behavior from what we saw for the original potassium-doped barium 122. Okay, so we were able to study the superconductivity in detail, ARPES, STM, tunnel diode, Mossbauer, but then we wanted to see if we could modify this state and push a little further. Okay, Remember, I invoked the barium, potassium, iron 2 arsenic theory. If we have 50% potassium substitution, that puts us at this part of the phase diagram. Well, 50-50 barium potassium is the same electron count as 50-50 calcium potassium in this true quaternary material. If we take that as our inspiration, it says if we're able to add electrons, we're able to then move backwards, and we might be able to discover the magnetism or the structural phase transition or the whatever that this superconductivity is coming from. So this led us to go from 4 to 5. We wanted to go to a quinary system where we were doing cobalt or nickel substitution on the iron side, okay? So we were able to do this for cobalt. As we add cobalt, we can see that we suppress superconductivity in the magnetization, we suppress superconductivity in the resistivity, and in the resistivity, we see a new feature kick in as we add more and more cobalt, seen clearly in the derivative, okay? We can do the same for nickel. As we titrate in nickel, we suppress the superconductivity in the magnetization, we suppress the superconductivity in the resistivity. Again, in the resistivity, we see this new feature come in and move up. We can see this new feature in specific heat as well. Now, if we take those data and plot them together, we see several things. First of all, the temperature doping phase diagram for cobalt and nickel is identical if you scale these by a factor of 2. This is very similar to what we saw in the barium iron 2 arsenic 2 materials, that electron count is key, okay? Secondly, there's a new phase line here, and we were able, through detailed measurements of NMR, Mossbauer, structural transitions, thermal expansions, ultimately neutron scattering, identify this as a new type of magnetic order for the iron arsenide, something called a hedgehog spin vortex crystal, which very importantly has no structural component to it, so no nematonicity. So the basic message is, if you want to have a new materials physics research endeavor, you want to have multiple motivations. You want to be looking for specific compounds, specific ground states, and keeping your eyes open and sometimes explicitly inviting the unknowns to come to visit. You need to have an adequately broad research focus to be able to do this. If you have a very, very limited research focus, this then is not possible, and you're more in a sort of applied research mode. Okay, this is a very basic research mode of operation. Okay, and fortunately, DOE and BES have been the premier funding agency for this for my 30-year career, and they have really been heroic in their support for this type of new materials discovery and synthesis. So let me end with the same conclusions, but then add 2 more. We need to be both humble and ambitious as we go forward, okay? Humble in recognizing there are many unknowns that can only be discovered by broad, discovery-oriented, experimental synthetic programs, okay? But we also need to be ambitious. We need to strive to make these discoveries more frequent by taking advantage of all the new experimental and computational and theoretical advances. And I'm really hoping in my own research to be incorporating computation more and more. Some types of transitions, like collapsed tetragonal, computational can just nail. They're not that difficult, okay? On the other hand, the fragile magnetism and other things are still tricky, and we still have work to do. So I thank you so much for your attention, and I will happily take whatever questions you have.
Well, let's first start by thanking Paul. And there were so many things that Paul raised there. We should have a wealth of questions coming out. But let me begin by opening the floor with a question from Daniel Komsky, who asked if he could ask a question. Daniel,
Hey,
yes.
You described the story, how did you look for heavy fermion material marked praseodymium. Okay, fine, very nice story. And now I have one general question about this related thing. We know that heavy fermion materials and mixed valence systems among rare earths are observed when we have known two valence state, like cerium 3 plus, cerium 4 plus. Or maybe praseodymium can also exist both as 3 and 4, or maybe thulium 2 and 3, terbium 2 and 3, and so on. Now, all this fine. There is one strange exception: terbium. Terbium chemically is known to exist as 3 plus and 4 plus. It's pretty stable, pretty well known. And nevertheless, I don't know a single compound of terbium, compound or intermetallic compound or whatever, which would have something like mixed valence or heavy fermion. So my question is actually for a long time already: what's wrong with terbium?
Well,
Maybe you know something.
Let's be careful, because chemists can be very perverse or aggressive in the environments they need to stabilize valences. So, you can say the noble gases, some of them aren't as noble as they pretend to be. You can form compounds with xenon and other ones. My question is, for terbium, TB, has tetravalent state ever been stabilized in a metal, or is it a highly oxidizing, insulating compound?
At least it's known in some chemical compound. What it's doing in intermetallic compound or in alloys, I simply don't know.
Okay, well,
but usual kind of trend, usual systematic is that if chemically the known element known to exist as 3 plus and 4 plus, like cerium or maybe even praseodymium, or 2 plus and 3 plus, like europium, samarium, or terbium, thulium, they always form something like mixed valence or heavy fermion material, at least sometimes, at least in some combinations, except terbium.
But again, a heavy fermion material needs to be a metal. And if terbium only has this rather exotic tetravalent state in wide gap insulators, then that's interesting, but you'll never be able to see a heavy fermion, because heavy fermion physics is metal physics. My answer to your question of what's wrong with terbium, why don't we see it? It may be the conditions to get it to this ambivalency are just too extreme. That would be my speculation.
It would be nice if someone would try really, because I'm really surprised why there is no single intermetallic compound which would show something strange for terbium.
Okay.
I don't know.
Thank you very much, Daniel. Adroija had a question here. Do you want to ask your question, Adroija?
Just want to know about the crystal field. Are there any study on the quasi-crystal, crystal field excitation? How do they look like?
I'm sorry, I didn't understand. Studies of crystal field in what system?
Quasicrystals.
Yes, Alan Goldman and co-workers have done some studies, but one of the difficulties is in the quasicrystals, you need to solve the 6-dimensional crystal structure and see how many unique crystallographic sites there are. And unfortunately, in most of the quasicrystalline systems, there are multiple crystal sites, okay? That then makes the analysis of it quite difficult, okay? Now, I believe that they were able to successfully do some crystal electric field studies in the rare cadmium systems. And I think some of the Japanese groups that have also been looking at these rare cadmium approximates have looked at them as well.
Okay. Can I invite other questions? Yes, Gunnar Muller has a question. Gunnar, do you want to come up?
So yeah, it's a little bit of a heretic question, maybe. I mean, you've showed us such a wealth of insight and a diversity of ideas that really feeds into this work of materials discovery. But I mean, there has been some push to actually use machine learning and actually, sort of gather this wealth of information and formulate new kind of strategies to find it without actually requiring so much insight on the human level. But I think one of the underlying requirements for that is you have to actually look what sort of metrics are useful, and then maybe gather some data as to how those metrics vary over the space of materials. I mean, would you have any strategy in mind that you would pursue? Or, I mean, what do you think are the most important features that you would look at to facilitate that sort of search, maybe as an assistive technology to make your life?
For example, for high TC superconductivity of the ilk of copper or iron based, or even the old-fashioned heavy fermions. I hoped I outlined it in the talk. So I would think that the most promising thing to do would be to look for fragile magnetism nearby, and then use that as a way of trying to look for the superconductivity. Now, I do warn you, having spoken to people who do machine learning even on simpler systems like electron phonon mediated superconductivity, and there's sort of for me, there's a fine line between data mining and machine learning. Okay, so if you have to forgive me if I blur these a little. But I asked the question of, look, in the year 2000, if we had the data from the year 2000, would your machine learning predictor find MGB2 with a TC of 40 Kelvin? The answer was no. It's good at finding stuff that is known to exist, but it is absolutely unable to find the complete surprises. Now, maybe we'll refine beyond that. So we know that you have high TC superconductivity in cuprates and arsenides. I would say maybe we can find other examples, and I would desperately love to find cobalt or nickel by looking for a small and tunable sized ordered antiferromagnets that then we can perturb either with doping or pressure. Now, that's a very specialized answer. But again, for a specific ground state, you need to sharpen the criteria you want to invoke. So, for example, I'm very interested right now in looking at these collapsed tetragonal transitions that we first saw in calcium iron 2 arsenic 2 that had been appreciated chemically for 15 years, but are becoming more obvious and appreciable with pressure or strain. This is something that I think computationally we can try to find by looking for depletion of anti-bonding levels associated with nictide bonding. And this is something that Rosa Valente's group and I have been doing. But again, you need to understand the physics of the specific problem and then come up with sharp criteria for that specific state. Now, I don't know if I answered your question. If not, please ask it again and hold my feet to the fire.
No, I think it was an insightful answer. Thank you.
All right.
Good. Let me follow up on that, if I may. One thing that's clear is that material space is a vast universe, so of course some of the things that you've done are published, but there must be a great deal of data that you have, which is only known to your lab, and this must be repeated in materials labs across the world. So my question to you is, what thoughts do you have on how we might better share data in this community, and in particular share the result of failures, because dead ends are also important. If you had a machine was trying to learn, it would need to know the dead ends as well.
Absolutely.
And we need to know those too. So you must have tons and tons of synthesis attempts that didn't work out.
Oh no, Piers, everything I try works the first time. You can ask on me.
Okay, good. So have you any thoughts on how we should record that information?
Yes, I do, but unfortunately, I'm going to be a politician and answer first the question you did not ask.
Okay.
And, you know, in the abstract for this talk, as well as on the first page and whatever, I refer to this review article, New Materials Physics. In that, so I recommend it to all of you in the simple sense that there's a lot of good jokes, good stories. It's very light and fluffy in its writing, but it has some very serious points. And at one point, I point out that all of you as referees, okay, need to pay much more attention to groups that say single crystals of this material were grown using the flux method, period, and provide no further details. Or single crystals were grown by and no reference, okay? That is antithetical to the scientific method, okay? In my group's papers, I do things that I have been scolded by colleagues as just being ridiculous. In the very first paper for MGB2, the first paper published on superconductivity of MGB2, I gave detailed instructions of how to synthesize it. In the very first paper on the rare transition metal 2 zinc 20, a whole family of materials, hundreds of different members, okay? I outlined exactly how to handle zinc and how to grow these in detail. Now, I think that's the way the scientific method should work. But the problem is there are colleagues around the world, okay, who then grow it exactly the same way, even incorporating perversities that I did just because I felt that way that day, and give zero reference to our work or other people's work. And the reason I went on the screen, Piers, is if you want people to publish details, the community needs to treat the first growth the same way as the first discovery of a property, and it needs to be cited.
Yep.
Now, if you do that, then you may also have people publishing their failures. But unfortunately, synthetic groups have this sort of prize-winning recipe for pumpkin pie at the local county fair. Oh, that's my secret recipe. If I tell other people, they may be able to be as known for good pumpkin pie as I am. And that's a mentality that exists, unfortunately, in many synthetic groups. So you're dealing with a psychological problem here. And you know, I've been publishing, my feeling is with the first discovery, it's your obligation to publish lavish details on how you synthesize something. But many of our colleagues and many of the other groups do not. And unless that is handled by referees insisting that, come on, you need to give more details, or you need to cite, or you need to do this, it's not going to happen. Okay, now, that's an obligation on everyone listening. Okay, now, how do you get null results published? Well, again, it needs some either repository or look, in the old days you had in PhysRev B, brief reports. They got rid of it because people kept using it as a trash can for rapids that didn't make it as PRLs, that didn't make it as letters to nature. I actually liked brief reports as a place to put a brief report. So I would have loved to put some report that we tried magnesium iron to arsenic to. 1 or 2 paragraphs, 1 or 2 figures, that's it. It's a brief report. That gets it into the literature. Sadly, that doesn't exist. So it requires some difference in how to publish data or how to curate it. But, you know, it really is incumbent on the field to both insist on synthetic details, but then also to insist on proper referencing of them. Because I can't tell you how many times I've seen a growth exactly the way we did MGB2, or exactly the way we did rare earth transition metal 2 zinc 20s, or the 1144s. That's a super limited phase space. We spent months doing that. We published a separate paper on exactly how to do it. Now I see groups over the world just using exactly the same compositions and temperature profiles with no reference. And that's not good for the field because they're not providing the details. and they're not giving the citation. So I think you're going to have to deal with a rather complex difficulty here, Piers. It's important. I would love to do it, but it's going to require the field to appreciate that for condensed matter physics, figuring out the growths are as important as figuring out the measurements. Okay, since we do both, we're in a good position. Sorry, that's a long answer and you invoked a screed, but I think
actually, it's a very good answer. Thank you. A lot of issues there that you bring forward. Okay. Well, more questions. Oh, quite a few questions back here. Okay, come forward. Yep. You're next. Say your name.
Hi, Paul. My name is Hector. Thank you very much for an interesting talk. I was just curious, when you think of a new compound that you might want to synthesize, you must presumably run into some issues of actually how to go about it, given the vast range of different compounds that you want to make. So, what sort of challenges, and just from the synthesis point of view, might you run into?
Okay. So let me make sure I understand. You want me to discuss issues of volatility, toxicity, reactivity, crucible stability, or do you want something else?
Just sort of the different methods, the range of different methods maybe that one might use in growing certain compounds. Let's say if you want to change one element in a 4-element compound, let's say, would you be confident that you could grow it the same way that?
No, I'm never confident of anything. And I don't say it sarcastically. It's just, at a certain point, you can hope to do things. So let me say it this way. So let's have a rare earth XY compound. If the rare earth is gadolinium, I feel fairly confident that I can probably substitute in a terbium, dysprosium, maybe samarium, neodymium. Okay, those are the nearby lanthanides. Chemically, they're similar. Sterically, I'm not changing things too badly. On the other hand, if you say for the rare earth, do I think I could put in sodium or strontium? Maybe not, because that's a change in valence and it's a change in size. If it's a silicon-containing material, I think that maybe I might be able to get germanium, but not always. If you say, no, I insist that you substitute in tin or gallium or something else, it doesn't necessarily work. So part of this is really experimental. I have experience with probably over 10,000 growths in the group at this point. We have some intuition, but honestly, you always need to check experimentally what works, and if it works, you rejoice, and if it doesn't, sometimes you discover something else, sometimes you reach a dead end. And sometimes, going back to Piers's question, sometimes the dead end is so trivial that it's not worth writing up at all. On the other hand, sometimes the dead end is sort of noteworthy. Now, other difficulties are, by the way, are you a theorist or experimentalist?
Experimental, but I don't do crystal.
No, but that's fine. Sometimes it's issues of toxicity. You need to be very careful. Arsenic and selenium aren't that kind to you. Sometimes it's volatility. Look, zinc, so when I teach a course on new materials growth, this is a different summer school. In the middle of it, I play a game of eat, wear, or kill. And it's the oxide of this material. Do you eat it, do you wear it, or does it kill you? And, we do various rounds. So, bismuth, eat, wear, or kill. Well, you're supposed to answer.
Me?
Bismuth oxide, eat, wear, or kill?
Eat, wear, or kill. I don't know. Where, I guess?
Yeah. No, it turns out that's eat. Pepto-Bismol. Bismuth is soothes the stomachs of ruminant animals and humans. Beryllium, eat, wear, or kill?
Where on that one then?
Holy shit, no, kill, beryliosis. Lead, eat, wear, or kill.
Well, where? I have to keep, I'm a one horse.
It's all of them. It's eat, wear, and kill. Lead oxide was sometimes called sugar of lead. It's sweet. It's why lead paint is dangerous, because little kids think it's yummy and sweet. One of the queens of England, Elizabeth, had so much thick white cake lead makeup on that it caused problems. And of course, it kills you. But zinc, eat, wear, or kill, that one you wear, zinc oxide and sunscreen. Okay, so again, these are all worries you have. So when we were trying to figure out how to handle zinc, it has a vapor pressure, it can blow up the ampules, it's volatile, but fortunately the oxide is non-toxic, so we're not worried about that. On the other hand, with arsenic, it's volatile, it can blow up, and it can fill your lab with a white smoke that is very toxic. I have avoided that. I have colleagues who have hadn't, and that had their lab shut down. So these are concerns as well. New materials growth is a combination of many, many concerns. Am I addressing your question?
Yes. Yeah, I suppose another sort of angle, I suppose, to my question was, if let's say you failed to grow a certain compound, could it be maybe that, the reason for the failure might be that the compound doesn't like to form in the first place, or whether it was just the sort of method you went about trying to synthesize?
Yeah, and that's a very salient question, and it's a other answer to Pierce's question. Okay, so we tried to grow calcium iron to arsenic too. Why didn't we put that somewhere? Well, we failed to grow it using the techniques we had. It could be that if someone uses vapor transport rather than solution growth, they might succeed. It might be that people can succeed in other ways. And you're really only able to state you failed to grow it in this very specific, limited way. And again, there's sort of a hesitancy because, yeah, you can explain it, but then you're sort of putting a mark out there that, oh, Canfield wrote he couldn't grow it. Well, we can write it and say Canfield's wrong. I'm old enough that I've been wrong about many things. I can live with that. But there's, again, a bit of a disincentive. So that's another issue because you're never sure if you just didn't do it the right way or find the magic region or whatnot. So, it's hard to prove a negative is another one.
That's definitely true. Well, thank you very much.
Thanks so much.
My pleasure.
Next question. Oh, okay, yeah, there's one on the screen. George Wood, would you like to ask a question?
Sure. I was just, can you explain how these solution-based growths are used to kind of access these inaccessible regions of the phase diagram, which are kind of buried underneath everything?
Yeah, let me go back to the paratectic. Let's see. Where is my screen? There we go. Sorry for this bouncing around a bit. Back. I'm just going to platinum tin 4 because that'll serve well enough. Here. All right, so here's the platinum tin 4 phase diagram. So this is a standard binary phase diagram. You have pure platinum and pure tin. Let's look at platinum tin 1,1, okay? This is what's known as a congruently melting material. This is like the elements, okay? What it means is I can go from a homogeneous liquid of platinum tin to a homogeneous solid, and it happens, boom, at a well-defined temperature, in the same way that H2O goes from a homogeneous liquid called water to a homogeneous solid called ice, okay? That's what we're used to, okay? Most materials don't behave that way, okay? So, and that's just a statistical statement, okay? So let's take platinum tin still, okay? If I warm this up, it's platinum tin, it's getting warmer, it's platinum tin, it's getting warmer, and now, boink, it's a liquid, okay? Let's look at one of these guys, okay? Let's take platinum 2 tin 3. Let's magically have a solid of it, okay? We bought some, okay? I can warm it up. It's getting warmer, it's getting warmer, it's getting warmer. And now at this temperature called the paratectic decomposition, it doesn't become a homogeneous liquid. It becomes platinum tin and this liquid. And as I heat up more, I have platinum tin, but more and more of this liquid of a changing composition, okay? Only when I get to this temperature, above this, do I have a homogeneous liquid that is 2 platinum and 3 tin. And as I keep warming up, I have that, okay? Now, the implications of this are more profound when you cool down. If I cool this down, I hit this liquidus line, I start growing platinum tin. The liquidus line tells me what the composition of the liquid at a given temperature is. All this cooling, I'm getting more platinum tin and the liquid is becoming more tin rich, okay? Now, when I drop below this paratectic, I start growing platinum 2, tin 3, okay? And I still have a liquid that's becoming more tin rich. I'm now growing and it's getting more tin rich, and now I'm growing platinum tin 4, okay? That's how you read a binary phase diagram, okay? So how would I grow platinum 2, tin 3, okay, without all this other crap? Well, I'd have to start with a composition that's more than 75% tin, okay? Then I have a homogeneous liquid. I start growing my platinum 2, tin 3. I cool down, and I better stop the growth before I cool below 745. Okay, how do I stop the growth? Well, I yank the crystals out of the liquid, or I remove the liquid from around the crystals, and that's what I tend to do. I have a filter, and I dump them into a centrifuge, decant, and get the crystals. So these incongruently melting compounds, these are the ones that you say are sort of hard to reach regions. And that's the whole philosophy of trying to grow platinum tin 4 or other deep paratectic materials. On the other hand, you just need to figure out where this paratectic hits the liquidus, and then you can slip it underneath it and grow the material. And as you can see here, you get beautiful crystals. So the essence of solution growth is finding where the liquidus line or surface is and intersecting just that. And that's quite an experimental difficulty all by itself. Now, since I'm a physicist, I use this as a tool to get me the samples that I can then do my lovely thermodynamic and transport measurements and get the physics. Okay? So it's very much the same way that you can say, oh, well, computational people, they sure know computer programming. Yes, they use computer programs to get results, but then as physicists, they try to extract out the important terms and understands what's going on. So, you know, I am an amateur crystal grower, a very good one, who happens to do this to get at the physics I'm interested in. Okay? But did I explain how you identify and get to these forbidden regions, or do you want me to elaborate on something further?
No, that was great. So you're just accessing the correct part of that liquidus line, and then
let's go back to further down where we can, like Abbott and Flatland, go to higher dimensions. Okay, so let's go to these two poor lads. Yeah, here we go. So Ty and William, you know, we're trying to grow calcium, potassium, iron 4, arsenic 4. In that case, you don't even have temperature shown. This is just composition inside the volume of this three-dimensional space. Now, we can reduce this to a pseudo-ternary phase diagram where we have iron, arsenic, calcium 122, potassium 122, and what we want. Okay? That the region in composition that allows us to grow this is way the hell over here. Okay? That's way, way over. Okay? But this is where, as you cool down, so as you sort of drop down in temperature, that if you intersect here, you can start growing the right material. Okay? So it's a tricky business. The exposed liquidus you want to intersect isn't always close by to what you want. And look, that's sort of a trivial statement. I showed you with platinum tin 4, we're growing this 2080 material all the way over at 496. Okay, so.
Very good. Further
Thanks very
question.
much.
Further questions? I think. Any more questions? Yeah, come over. Yeah.
Hi, Paul. It's Peter Wahl from St. Andrews.
Hey, good to see you.
I have a quick question on the optimization of the growth. So for metals, you showed a couple of times that we can use the triple R, and that's a fairly straightforward way if you have two crystals of the same materials, as far as I understand it, to say one has less defects than the other. Is there a similar measure one can use for insulators? And I think the question is partially in relation to, for example, materials like samarium hexaboride, where there's been a lot of discussion about the role of inclusions, about polarity and things like that.
You see, yeah. Look, the devil is in the details, always, because triple R itself, no, you can leave your mask off. I don't feel threatened. The devil's in the details. Okay, so triple R in metals is, quick and dirty, but it doesn't tell you everything. For example, you mentioned inclusions. Triple R doesn't tell you much about inclusions. As a matter of fact, I can have a cerium antimonide. I can get triple R's of 1,000. They're great, but if I'm not careful, since I grew it out of tin, I can get triple R's of 10,000. But what I'm measuring is filamentary tin as an inclusion, and that can lie to me. Okay, so again, devil's in the details. So for insulators, okay, you said insulators, let's start with semiconductors, okay? So a semiconductor, if it's a simple semiconductor, it's how long you can get an Arrhenius behavior with a large gap that you don't roll over into an impurity band or something like that, okay? That's what we were seeing, for example, when I looked at cerium-3, bismuth-4, platinum-3, which I think is still the cleanest condo insulator, okay? Now, samarium hexaboride, that's true, but you can also say that some people think that it rolls over into this flat band that Megan and others saw that's associated with a topological state. On the other hand, you worry about inclusions. This is one of the reasons why I've sort of adopted a peeve that Ivan Schuler had for a long time, is when a paper says, and the triple R of 10 shows that we have high quality single crystals. Okay, well, high quality is very ill-defined, and you need to define what the quality is for the measurement you have. So for insulators, a trivial insulator, I would say it's the range of a large gap Arrhenius behavior. But on the other hand, inclusions can hide and cover a lot of sins. With condo materials, even dislocation lines can be a problem. We showed with ytterbium, nickel to boron to carbon, that you can anneal out dislocations, and just the Burgess relaxation vector around the dislocation line can give you distributions of condo temperatures that change the resistance dramatically. So quality is defined by the physics you're after. So yeah, sorry, it was a long rambling answer, but for a simple semiconductor, the equivalent of triple R is, the inverse of it, how long you get your Arrhenius behavior. But if you start invoking special physics or start worrying about inclusions, which then are resistors in parallel and series, it becomes a lot more difficult.
Yeah,
So
okay.
is the answer.
Yeah, thanks.
You bet.
All right. I think we've reached the hour. We could carry on talking for hours and hours, but I think this is a very natural point to break away.
All right.
I want to thank everyone for coming. I want to particularly, all of us, let's thank Paul one more time. Thank you, Paul. And I'm coming over to grow some crystals in your lab soon, Paul. I'm looking forward to it. Hope at one of these times I'll have a go at it. In the meantime,
I have actually invited and had people. Oh, by the way, if you want, Piers, look at Nova. David Pogue's a host there. He did 2 hours on the periodic table. I had this guy in my lab, and in 2 hours, I taught him how to blow quartz and There's film of him in my lab yanking something out at 1200 and decanting it. It's like 3 minutes. But it's a summary of what we do. So you can find, if you can't find it, I'll email it to you, okay?
What particular NOVA program was that? Do you remember?
I think it was called the periodic table, but you can just do a web search on Paul Canfield NOVA or something, and you'll see something.
Okay, very good. We'll look for it. Thank you.
All right,
Very
take care.
Okay. Bye-bye then. Thank
Bye.
you very much. Bye. We'll stop the recording. Stop the recording. Oh, accepting. This has now gone out under. I can't stop the recording because I'm not the host anymore. What do you do when you're? I tell you what, I need to take